Hey folks, one last lecture before we get into some worked problems. This itself is a bit of a worked problem, but I wanted to talk about a very specific concept through this worked problem. So it's kind of a transitionary lecture, I suppose. And that is that we need to conserve momentum in both directions, x and y. Honestly, in all three directions, x, y, and z. But the third dimension, z, is not a direction we normally work in this class. We're going to change that in chapter 12, but I wanted to work an example that looks at conserving momentum in two dimensions, in both directions, x and y. So we're going to be able to do this by looking at a perfectly inelastic collision. We have two balls of clay that are colliding and moving as one object after the collision. Ball 1 has a mass of 10 kilograms and an initial velocity of 2 meters per second in the positive x direction. Ball 2 has a mass of 8 kilograms and an initial velocity of 5 meters per second in the positive y direction. What is the system's final velocity as a vector? And we've kind of already seeded the expectation that we're probably going to work with a magnitude and a direction, meaning an angle here, just based on the fact that we have a VF and a theta. We could work with VFX, VFY. That's perfectly fine, but I think doing the VF and the theta is quite appropriate as well. So to start this problem off, we're asking ourselves, is this isolated, right? Is this isolated? And the answer is yes. There are no walls. Honestly, when we think about non-isolated situations, we're thinking about interactions with objects like walls, ceilings, floors, the ground, maybe a table that is, bolted to the ground. Things like this that are part of a larger, more complicated system. That is indicative of a non-isolated situation. But here, all we have are two balls of clay colliding and moving as one. So it is isolated. Yes, indeed it is. All right, so we are conserving momentum as a vector. But this kind of means two things, right? It means that we are conserving x momentum and we are conserving y momentum. If we think about this, we have two balls of clay coming in at 90-degree angles, but with different masses and different velocities. So we're going to move off in some angle, right? Some angle theta off of the horizontal here that conserves momentum in both directions. So I think let's just start off by looking at what we have in the x direction. Right? So let's say px here, right? For px, we are saying that we have m1 v1 I plus, that was our m1 momentum. Does m2 have any momentum in the x direction? I don't think so. It doesn't have any component of velocity in the x direction. It's only in the y. So we're going to put 0 there. And so that was all the initial, right? That was initial momenta. Now we're going to say the final momentum, right, is m1 plus m2 because they have collided and moved together now, times vf, but specifically vf, and we're going to have to say cosine of theta. This is the VFX portion here. If we were to draw out the components, right, I have a VFX and a VFY. So this is our final momentum in the x direction. We could do the exact same thing for the y direction, right? In the y direction, I don't have any initial momentum in mass 1, but I do have some in mass 2, m2 v2I. That has to be equal to some final momentum, m1 plus m2 times vf sine of theta. And again, initial, final. So at this point, we could actually start to solve, right? We could start to solve vf and vy. I think that might be something that we could do, right? vfx and vfy. Let's change my eraser to a smaller one here. What we're also saying, if I zoom in a little bit, this is also equal to m1 plus m2 times vfx. This is also equal to m1 plus m2 vfy. And so if I'm solving for vfx, vfx equals my m1 v1I over the sum of m1 plus m2. And vfy is equal to m2 v2I over the sum of m1 plus m2. Now the reason that we're doing this is we're trying to find vf, right? And we don't know thetas yet. If we knew thetas, this would be pretty easy. Now, you could have solved for, theta, then plugged into one of our other equations here, solve for theta in the x direction, plug into the y direction, solve for vf. I think that's unnecessarily complicated. You're going to have to work with inverse sines and inverse cosines. I think I'd rather build it up as a vfx, vfy component business here. When I plug in my numbers, I get vfx equals 1.33 meters per second. vfy, I get 2.67 meters per second. Let's just take a look. Does that make sense? Well, I do think that m2 and m1 are pretty close in mass, but v2 is over twice as large as v1, right? So I do think it would make sense to have our y component be larger than our x component. I think that makes a lot of sense there. So if we were just looking for component component form of the vector vf, right, I would write it as, right, 1.33 I hat, comma, 2.67 j hat, close that, meters per second. That would work. But I said that we wanted to probably find theta as well. So let's find theta. Theta, if we have vfx and vfy, theta would be the inverse tangent, right? Theta would be arctangent, atan, tangent to the -1. That's all the same thing. It's inverse tangent of vy or vx. What I get is 63.5 degrees. And again, I think that makes sense with the components that we have. I think the last part, if we didn't want to just write this as a component vector, but rather as a magnitude and direction, is to take the magnitude, right? Vf as a magnitude would be the square root of Vx squared plus Vy squared. We know that. And I get a magnitude of about 3 meters per second. So we could say that it's 1.33 I hat, comma 2.67 j hat meters per second, or we could say that it's 3 meters per second at 63.5 degrees above the positive x-axis. Both of these are vector form. I kind of like the second one just because I think it gives us some information about truly how fast is this moving, what's the speed, as well as the angle that it's moving at. So I like that a lot. That is how we would approach conservation of momentum in two directions. You want to conserve momentum in both directions, but usually there's some interplay between the directions. So usually through the angle or through the final vector. So that's just a brief walkthrough on how to do this. The next 2 or so videos are going to really just focus on working some problems, probably more in one dimension than not. So that's that. Have a good one. Let me know if you have any questions in office hours or in my email.